Everyone, welcome back to my YouTube channel. I am Ranjitha.G, currently studying in Sri Venkateswara College of Engineering, Bengaluru. I am from Department of Computer Science and Engineering. The section is Chanakya. The course title is Data Structures and Applications. The topics which we are going to discuss today is future-based persistent spatial data structure for NVM-based Manicore machines. The contents which we are going to study today is introduction, background and motivation, current limitations of FPR tree, problem definition, MPR tree design, evolution and conclusion. Introduction. Non-volatile memory (NVM) is a type of computer storage medium that retains data even in the absence of a power supply. The NVM is a type of a data storage. It acts as a storage of data even in absence of the power supply. The semiconductor technology used to build such devices ensures that a continuous power supply is not required to retain the data or program code stored in the device. Some examples of non-volatile memory is flash memory, magnetic storage, and certain types of read-only memory that is known as ROM. Background and motivation. Here we can see the graph of number of threads versus throughout the KOPS. Here we present the background of FPR-tree followed by how existing index data structures addresses the concurrency limitation and NUMA effect on Manicore machines. In background on motivation, we can see that the background of FPR-tree is followed by index data structures address and the concurrency limitations of the Manicore machines. R-tree is one of the most popular spatial index data structures used in databases. The R-tree is one of the most popular spatial index data used in databases. To store multidimensional data objects with the emergence of Manicore machines, the use of Manicore parallel programming is also essential in the background and motivation of a MVM. Current limitations of FBRG. Here the limitations of decision tree modules. The mechanisms are not fully understood and therefore the technology needs to be tested on a pilot plant scale. For every small or low density carrier media, the solid holdup decreases rapidly and a particle iteration becomes severe as the gas flow rate is increased. It is also inability to capture the complex relationship. The other limitations are of the FPR tree is overfitting, high variance, bias towards the dominant classes, inability to capture complex relationships, greedy nature, lack of robustness to small changes, not ideal for the high dimensional data. These are the limitations of decision stream modules. Problem definitions of MPR-tree or FPR-tree. Here, the FPR-tree faces a performance constant where executed in high degree of concurrency, and this is due to its design and development choices. Here, the problem definition defines that the FPR trees faces a performance constraint when it is executed in high degree of concurrency. This is because its design and development choices that it chooses for the performance. The simplest technique to ensure correctness in index data structure is to obtain a lock on the shared data and allow only one thread to write at a time. The simplest technique to ensure correctness is in index data structure we can obtain a lock on the shared data and allow only one thread at a time. FPR-tree also supports the lock-free read operation and relies on atomic metadata update operations for the correctness of the data structure. FPR-tree also supports the lock-free read operation and it relies on the atomic metadata update operations for the correctness of the data structure. Here we can see in the graph problem tree analysis gives to objectives tree. It chooses the strategy and it gives to formulates the log frame and it verifies the project's design. Here we can say that the problem definition of the FPR tree is this. MPR of a tree design. Here we provide an overview of our proposed MPR tree followed by operational flow, correctness guarantee and NUMA awareness. The design objectives of MPR tree are to achieve concurrency, crash resilience and NUMA awareness while maintaining the read performance. The tree design of a MPR, here we will prove that the proposed MPR tree is followed by operational flow, correctness guarantee, and NUMA awareness. The design objective of the MPR tree is to achieve the concurrency, crash resilience, and NUMA awareness while it maintaining the read performance. And our solution is composed of three components that is divided into DRAM and DCPM. Here we can see that MBR is divided into MBR1 and MBR2. MBR1 is divided into MBR3, MBR5. MB2 is divided or classified into MBR4, MBR6. This is the structure of that acquire lock on a way to the acquire look. Evolution of a FBR tree. In FBR tree, a thread only acquires the lock on a subtree until it enlarges the after node where the new spatial object will be inserted. In FBR tree, a thread only acquires the lock that a subtree until it enlarges the after node where the new spatial objects will be inserted into it. Even though the FBR tree adopted the fine-grained locking mechanism, it will suffer from lock contention. Even though the FPR tree is has adopted the grained locking mechanisms, it will suffer from the lock contention. TLFOS are the main component of our design. For evolution, the main component of our design is TLFOS. The it plays a significant role in application performance. MPR tree with hash first has to check the hash table and then look for the object in the corresponding TLFOS. Object is used to check the hash table first and then it will look for the object in the corresponding TLFOS. Here are the graphs. Conclusion. In conclusion, we can say that the MPR tree, a highly concurrent persistence R tree for DCPM based many core machines. So, in conclusion, we can say that for MPR tree, the highly concurrent persistence is required. R tree for DCPM based many core machines. MPR tree is for highly concurrent persistence and R tree is for DCM that is based on the many core machines. To achieve the concurrency, we adopted the fine-grained locking over the state-of-the-art FPR tree and R tree variant for DCPM. To achieve the concurrency for the MPR tree, we have adopted the fine-grained locking system, but then also it will suffer from the locking contention. Such queries are optimized by the employing a volatile in memory hash table. Thus, in conclusion, the search queries are also optimized by the employing a volatile in a memory hash table. The search inquiries are employing a volatile in memory hash table that is used. Thank you for watching my video.